Now question 2 is asking us, oops, I'm just going to put that there. Question 2 is asking us to estimate the variance of xi from some sort of estimate, which is the one which is given there for v. So you want to check if expectation of v is going to be the same as the expectation of xi. And if it's not, we need to know how to bias it. So first let's check if it's the same. So v is going to be equal to, what is this? It's 1 over n sigma from I is equal to 1 to n xi minus, what is m? Small m, as it's given in the question, is the estimate of the mean from the previous part. So in the by the previous part they mean the question. So this is the estimate of the mean. Estimate of the mean is not expectation of xi, because we don't know what expectation of xi is. We just want expectation of m to be expectation of xi. But a variance of but the value m here, which is our estimate of the mean, is going to be the capital M which we see up there. J is equal to 1 to n xj divided by n. I'm going to make this better. Divided by n, the whole squared. I'm going to make this one slightly better too. X j, the whole square, right? But you can see this and you're going to realize that you're going to have to do a lot of calculation for this, a lot of algebraic manipulation. But we can try to make our life a little easier. We're still going to have a lot of work to do, but we can make our life a little easier by using linearity of expectation and the fact that the xi's are all independent of each other. So I'm just going to pull the 1 over n out over this, and this expression comes here, right? This sum comes there. But now we realize that each and every xi are independent and identically distributed. Therefore, this xi minus m term is going to be symmetric over all xi's. That is, it's going to look exactly the same for every single xi as a distribution. So since it's going to look exactly the same, expectation of all those quantities, of each and every one of these quantities, is going to look the same. So when you take linearity of expectation over and you pull the sigma out, you realize that it's just going to be n times any one of the expectations of those terms. So we're just going to pull another n out, and we're going to say it's equal to expectation of some xi, some arbitrary xi out of x1 to xn. So this is what it's going to be, because we know that each and every one of these terms look the same, right? This is just equal to expectation of xi minus, I'm going to drop the coefficient, I'll bring it back when I need it. Drop the limits, I mean. Bring it back when I need it, the whole square, right? So this is one step towards making things simpler, but now we're going to do a lot of hard work. Alright, so I just erased everything off because we're going to need a lot of space, and I've just written the important thing there. So all we're trying to calculate now is expectation of xi minus m, let's say for now, and we'll open it up when we need it. Expectation of xi minus m, the whole squared. From linearity of expectations, this is just going to be equal to expectation of xi squared minus 2 times expectation of xi m minus plus expectation of m squared. And this is going to be equal to expectation of xi squared remains the same. Now let's break out the m here. Whoops. Did I put 2 of them? Okay, which is equal to expectation of so first of all, you're going to see that there's going to be exactly one out of this sigma. Okay, I'm going to open it out first. Sigma xj. Why do my j's look like i's? Xj product, you have to multiply them, plus expectation of m squared. Let's deal with that one later. Expectation of xi squared, I'm going to just put this as ditto, minus, so we see that exactly one xi term, there's exactly one xi term in this sum, so let's pull that one out. See, it's 2 times expectation of xi squared over n, because it's exactly one term, plus sigma j not equal to I over n. Sorry, I'm gonna take this entire thing out because that looks weird. xi xj xj. So I just pull the xi in, and I'm going to divide every single term by n, right? So I pulled the xi into the sum, and exactly one xi over n is there in this, and I pulled that one particular term out of the sum, and then you have the remaining wherever j is not equal to I. I is no longer an index of a sum. I is just some arbitrary. I could have just chosen I is equal to 1. So I is just some arbitrary index which is not iterated over. So it's just alone and isolated. So over all j not equal to I, the inner sum is going to be xi times xj divided by n plus ditto, right? So now we have expectation of xi squared minus 2 over n expectation of xi squared, right? Plus we're taking linearity of expectation over this. So this is going to be, what is this going to be? This is going to be how many numbers are there such that j is not equal to I over n? We have 2 times n minus 1 over n expectation of xi xj plus, now let's open this out, expectation of sigma xi over n the whole squared, sigma xj. Keep getting confused with the indices. Now this is going to be equal to, let's ignore this for now because we're going to get another term like that outside, plus, so give myself more space for this, plus, so since xi and xj are independent random variables, we can split them apart, right? Because xi and xj are independent, expectation of xi times expectation of xi times xj is going to be expectation of xi times expectation of xj, just 2 times n minus 1 over n expectation of xi times expectation of xj. So this, now again, this xj is going to be some particular index. It's no longer, because I pulled out the sum because n of them look exactly the same. That's what I did in the previous step, because n minus 1 of them look exactly the same. I pulled out the sum and made it into a number, and therefore this particular j here is going to be unindexed. So I'm going to call this k, so that to avoid confusion, because it's just some arbitrary number, and it's no longer an index into a sum, right? Plus, now, oops, I'm going to pull out the 1 over n squared because expectation is linear. I can do this. Pull out the 1 over n squared, and I'm just going to deal with the sigma xj the whole squared. Sigma xj the whole squared, x1 plus x2 plus all the way to xn the whole squared, is going to have 2 types of terms. It's going to have x1 squared plus x2 squared all the way to xn squared, and then it's going to have x1 x2 plus x1 x3 all the way to x1 xn. Then it's going to have x2 x1 plus x2 x3 all the way to x2 xn. Now you see that every one of the x1 squared terms has exactly 1, right? Has exactly 1 of each type of term, x1 squared. But x1 x2 and x2 x1 have the same, where you have one index. When you have both the indices is different, you're going to have 2 of each of those terms. So every time I is less than j, as in you have xi times xj where I is less than j, you're going to have 2 of those terms, right? So I'm just going to take this entire sum and going to say this is equal to sigma, first I'm going to say sigma xj squared plus 2 times j less than L. I'm using a lot of indices, but bear with me. So this is where j is 1 and L is 2. You see there's j less than L all the way till n. That means j goes from 1 to n, or rather let's just say, instead of saying j goes from 1 to n, let's just say j is equal to 1 to n, and L is equal to j plus 1 to n. So for every single combination such that j is smaller than L, this is L goes from 1 to n, you have two terms which look like xj, xl, right? Put a ditto, oh yeah, and over here, okay, so I'm just going to, what I'm doing is I'm going to write an entire line, then I'm going to restart and then deal with every single term from the left to the right. Actually, no, that might potentially confuse people because I was talking about this. Okay, so I'm going to continue talking about this. So what I did initially over here was I pulled out each and every one of the x1 squared and x2 squared terms, and you get exactly n of them, right? So you have sigma xj squared, you have n of them. But over here, whenever I is not equal to j, for every I and every j, not for every I and which is for every j, okay, since we've already used j and l, for every j and every l greater than j, you're going to have exactly two terms. That is, over here, for these two, j is equal to 1 and l is equal to 2. So in this case, you have exactly two terms for every pair of numbers, j and l, such that l is greater than j and they're both less than equal to n and greater than equal to 1. You're going to have exactly two terms like this. That's what I've written here in this sum. Now, let's actually try to pull these out. Since you have n xj squared, it's a sigma of j is equal to 1 to n xj squared, and each and every xj squared is distributed the same. I can pull the sigma out and the sigma becomes just n times expectation of xj squared. Again, now j is no longer an index into a sum. It's just going to be some arbitrary number chosen from all those. And now how many, we can do the same thing for this sum as we did over here. We can do the same thing for this sum. How many different terms do we get when we have 2 times j is equal to 1 and l is equal to j plus 1? How many terms do we get? So when we see here, we see that the total number of terms is just twice n choose 2. As in, for every, we're choosing a pair of indices from n different indices, right? But then we have two different ways of doing them. So as in, we can have xi times xj or xj times xi. So it's totally n choose 2 indices times 2 for the ordering taken into account. So this is just going to be equal to 1 over n squared times 2 times, what is n choose 2, which is n times n minus 1 over n expectation of xj expectation of xl. I'm splitting these apart implicitly because those two are independent again, because now we know that j is not going to be equal to l from our assumption that l starts from j plus 1 and goes on. So we can split these apart because of the independence. So now we can cancel out a few terms. How do I get this? This is not an n here. This is 2. 2 and 2 get cancelled. N gets cancelled with n squared. Here an n gets cancelled with an n squared. So now let's group all the terms together. This is equal to expectation of xi squared minus 2 over n expectation of xi squared. And this xj squared is the same as xi squared, because since xi and xj are same, they're distributed the same, xi squared and xj squared are also going to be distributed the same. So this also, let's pull this in as an xi squared. So we have 1 minus 1 over n plus 1 over n. So we have expectation of xi squared of 1 minus 2 over n, plus 1 over n. Plus, now for these terms, how many do we have? We have 2 times n minus 1 over n. Do we have 2? Sorry, this is going to be a negative sign, right? Because we're dealing with negatives. I forgot to pull that out. So there's going to be negative. It's going to be negative. It's going to be negative. I should erase that, but I wanted to make sure that people know it's an error. If you're looking at this, I made a mistake there. Which is equal to expectation of xi times expectation of xj or xk, it doesn't matter. I'm gonna say xk plus n minus 1 over n expectation of xj times expectation of xl. So now we have I, k, j, and l here, but expectation of xi is equal to expectation of xk, which is equal to expectation of xj, which is equal to expectation of xl, which is all of this can be written as expectation of xi squared. So this is just going to be equal to, now I'm going to combine that to say it's 1 minus 1 over n expectation of xi. And since these two are the same and the coefficients, we have 2 times n minus 1 over n and plus n minus 1 over n gives us negative n minus 1 over n times expectation of xi squared. This is equal to 1 minus 1 over n is just n minus 1 over n times expectation of xi squared minus expectation of, how did this happen, xi the whole squared. That's how it happened. Yeah, so xi, expectation of xi times expectation of xk is going to be expectation of xi times expectation of xi, which is expectation of xi the whole squared. That's how I got this. So this is equal to, so we have expectation of v is equal to this thing here. I'm not going to be able to finish the box, am I? Oh, I was able to draw the box a little. Okay, that's good. So now let's deal with the end of it here. I'm sorry, this has a lot of work, and I didn't want to erase any part of it before I finished it off, and I somehow fit the entire thing into one screen. So what we remain with is expectation of v is equal to n minus 1 over n variance of xi, right? N minus 1 over n variance of xi. Now what we want to make sure that we don't have a problem with this, or rather we have a good estimate, is that we take whatever expression we had there and we said v prime is equal to n divided by n minus 1 over, not variance, over v. So our v prime is going to be just expectation of v prime is going to be just n divided by n minus 1 expectation of v, which is going to be equal to just variance of xi. So if we wanted to actually get a better estimate, we would try to multiply by this constant here. Now, does this make sense? What happens when n is equal to 1? Does this give us a good value? It gives us infinity. How does that make sense? How is that valid? Well, if you have only one sample point, if you have only x1, that is, if n is equal to 1, you only have x1, how can you tell anything about the variance at all? You don't know anything about the distribution. So how can you tell anything about how it varies if you have only one sample point? If I just give you one number and I ask you to tell me how that number varies and how the distribution of that number varies, you have no idea, right? Because you only have one number. So it makes sense in the sense that we have been giving us one sample will tell us absolutely nothing about the distribution, and it gives us some weird answer. It gives us infinity, right? Because potentially the variance of this could be a uniform distribution. You don't even know what this is going to be. And okay, uniform distribution, the variance is not infinity, but you don't know what the distribution is going to be. So given that n is equal to 1 and you only have one sample, it tells you that you're giving me no information, so I can't give you anything about variance. So it makes sense for the case where n is equal to 1. And yeah, that's it for part 2 of question 2.